Hello. I think we can start our session. I don't know. I will switch off that lamp. Okay. Hello. Thank you for joining me. If you can hear me and see me, you can use the chat box to say yes. Okay. Thank you. Good, good. I know probably you can always hear me and see me, but I just wanted to double check. Okay. That means what we will do, we will finish section 1.5 and we will cover section 1.6. Okay, that means let's start. Let's not, unless you do have some questions, some problems, some issue, maybe you can type it on the chat box and I can address it. If not, I can just start the session. Okay, I can watch the chat box, but I will change my screen. Okay. Oh, no, too fast. Okay, that's mean what we did. We did learn about, of course, the tangent line concept, but together with the tangent line, together with the slope of the tangent, we did learn the limit concept. And section 1.5 was about the limit of the function. Okay, that means I will go through the slides that we did yesterday. Okay, oh, it's my writing. That means we remember intuitive definition of the limit is just like an estimation, like an approximation of the function, like what function is doing near to a certain point. Okay, and then we did investigate how function x squared behaves at close to 3. Okay? That we remember exactly at 3, of course, the value is 9, but near to 3, the function, the curve is also approaching that level, and that level is 9. Okay. Oh. And we do remember I was telling you something like that this green 9 and the red 9 are a little bit different, okay? That means the red is exactly the value. 9 is the limit. The curve, the function is approaching that number. Okay. And then, just like a description of each component of the limit notation and the general definition. And I believe this was our last exercise, okay? And you probably remember I said it's quite important, even if looks like maybe trivial, which I hope, but it's extremely important because knowing the limit and the value for these 3 different cases, yeah, this means that you understand what limit means. Okay? That means you can pause the video later or you can look at the slides. Okay, and then let's start. I do have another example. Okay, this is from your textbook. That we have to investigate how function sine of pi over x behaves at 0. We may notice right away that x is in the denominator, which means it's not in the domain. Okay, it's not in the domain. And also you will probably think, oh, how can I investigate this? Yeah, would be nice to see the graph. That means I can tell you if the function is a little bit more complex. And another thing, we can't really do like an algebraic operation, which we will learn in next section. You probably have, you have to see the graph. And for this complex function, we will provide the graph. And let's look at the graph. Yeah, the graph looks interesting. That means how this curve, how we can read this curve. We can say it's like a sine curve, a little bit narrow, because of course it's just different because the pi over x change the values. But what is happening at 0? We definitely have no value. That means this function f of x defined as a sine pi over x is not defined at 0. Value at 0 doesn't exist. But we can still try to find the limit because we can look how function behaves. And I don't know if we can see, but function is kind of like jumping, like oscillating between, like when x is getting closer to 0. That means it's like jumping from 1 to -1, 1, -1, 1, -1. And it will be that it's getting closer and closer to 0, but will always like oscillate. That means the thing is, we do not have one finite number that function is approaching. Okay, because I can't just say, oh, the limit is 1 or -1, 1, -1. No, I have to simply say, okay, that limit is undefined. That we can see this is probably the first example that we may investigate the behavior of the function near a certain point, and we do not have like a finite answer. Okay, that means we may have cases like that computing the limit, investigating the limit, we will have no answer, undefined, because it's like jumping between -1 and 1 in this case. Okay, that means please remember, I think on the homework assignment we do have a few graphs. That means when you will see this oscillation, the limit is undefined. Because I can't say 1 or -1, no. Okay, then another example. This is another function. It's like a piecewise defined function. That we have different formula for different part of the x. That means when x is greater than 0 or equal to 0, the value is 1, just constant function. When x is less than 0, the value is 0. Okay, we can see constant line, horizontal line. And function is defined at 0 when it's 1. That's the reason that we have solid dot and the open dot. Okay, and of course, the question is how overall the whole function behaves at 0. Okay, we have to find out the limit, okay, limit of this function at 0. And what do you think? Do we have the answer? Does this function approach one finite number from the left and from the right hand side? The same number. Oh, yes, thank you for the answer. No, the answer is not. No, it doesn't approach, because we can see when I look from the left, that's actually right, from the right hand side, as x goes really, really close to 0, function is approaching 1. Yeah, the limit will be 1. But when x is approaching 0 from the left hand side, the value, the red line, it's approaching 0. Okay, it's at the 0 level. That means we don't have the answer. That means definitely, okay, definitely this is the answer and this is correct. However, the previous example was we had like this oscillation. And this is the good explanation, because what happened, as soon as we say that the limit is undefined, we have to have a reason. Okay, that means on this in this example we have two different behavior, two different values on the left and the right hand side. Okay, that means that's the reason. Okay, but how we can like state this, how we can indicate this. What mathematician, what they did, they develop the notation for one-sided limit, because as I just said, on the right hand side the limit is 1, on the left hand side the limit is 0, and that's sometimes really important information, because maybe we just want to know what is happening on the right hand side. or maybe on the other side. That means in this case, okay, we will have one-sided limits. Okay, that means as x approaches 0 from the left, okay, only, then f of x approaches 0 because it's the limit is 0. Yes, we can see that's the y value. And as x approaches 0 from the right-hand side, the function approaches 1. We can see the line is at the 1. This is 1 and this is 0. Okay, but how we can indicate this? And now let's look. We do have a special notation to indicate the left-hand side and the right-hand side limit. Okay, can you see? Can you see the difference? Can you just tell me that you can see? I don't know if it's tiny, but yes, plus and minus, yes, yes, thank you, yeah, I was just testing you, checking you. Okay, that's we can see the left-hand side, we will indicate with this, like a minus, sign, okay? And the right-hand side, we will always put like a positive. But also we will compute limits like that. But please, one thing that I want you, like, because the common mistakes, if we have more complex question, what you will do, you will sometimes think that, oh, when the situation is on the left-hand side, like everything must be negative. But please remember, that's not the case. Or if it's from the right-hand side, because of this plus symbol, we will think everything must be positive. Not really. That's when you have to be careful that this is just a notation. Okay, we still have to look at the graph, or maybe later we have to do some computation. Okay, which I can show you some examples. But just please remember, for now, doesn't mean that it's, of course, if it's a 0 from the right-hand side has positive numbers, 0 from the left-hand side has negative numbers. Okay, but even if it's different number, like for example, let's take a number line and let's take 2. Okay, and this will be the right-hand side, this is the left-hand side. That's how I will use the notation. And can you give me just a number which is on the right-hand side at 2? Close to 2. Can you give me any number on the right-hand side at 2? 2.1, really good, because we are in calculus class. We remember even better than 2.01. Okay, and can you give me the number on the left-hand side? Can you give me on the left-hand side? Yes, 1.999. Of course, we can go even closer. But what is my point? Both of the numbers are positive. Okay, that means this is just here, just to indicate this. Positive, even if I have this little negative symbol, this means just the left-hand side and the right-hand side. Okay. That means I just said this limit is undefined. And then we do have a definition, which probably is just the obvious output from whatever was said, that the limit of the function, okay, as x approaches a is equal to L if and only if right-hand side and left-hand side is the same. Okay, that means if one-sided limits are identical, then I can say, okay, then the limit exists. Okay, that means please, it's definition, and we will be using this naturally, like automatically, intuitively, we will not even think. Yeah, but that's the formal definition. I can say that the limit is L if the left and the right-hand side is the same. If they are different, then the limit of the function doesn't exist. Okay. And then let's look at this. We can maybe do this example really quickly. Okay, we have the graph of the function g, and we have to find a few limits. And I think okay. That's we can see the graph. Let's assume, I just want to ask you, what is the domain? You probably know the answer. Like, let's assume that this function is like, it's defined from negative infinity to positive infinity, but what is happening? And especially looking at the x2 and x5, do we have the value for the x2, x equals to 2? Do we have a corresponding value? No, we don't have the value. That means I can say this value is not defined, then x equals to 2 is not in the domain. And what about 5? Oh, I can maybe do this. Do we have the value? Yes, we do have the value for x equals to 5. It's 1 because we can see the solid dot. Okay, the solid dot. Yes, that means, oh, that's Micah, that's really good. Oh no, we can include 5 actually. From negative infinity to 2, and from 2 to positive infinity. 5 actually is in the domain. We do have something, it's happening, okay, but we do have value for 5, which means 5 is in the domain. You can keep but you can put the brackets. Okay, that's me now. Your turn. Get ready. Yeah, we do have that. Get ready, and you will tell me all of the answers. That means let's investigate 2. What is the limit of the function g as x approaches 2 from the left-hand side? Can you type it? It is 3. Yeah, we can see this function is, this is the left-hand side at 2, of course, and this graph is approaching the level 3. Did I type? Oh, I'm sorry. I didn't type. Okay, what is the limit on the right-hand side? Can you type? Yes, the limit, the limit on the right-hand side. We can see function is approaching dot dot on the right-hand side, and this is 1. Excellent. Which means, what is the limit at 2? Can I say, of course, the limit is undefined. And I can nicely say, this is my justification. This is my proof. 2 different one-sided limits, overall the limit is undefined. Okay, 5. What is the limit of the function as x goes to 5 from the left-hand side? It's, I think, because we just looking here, I think is that dot is 2. And what about the right-hand side? It's actually 2. It's the same. Yeah, we can see. I can possibly use different. It's approaching dots. Yeah, that's the right-hand side. That's the left-hand side. And it is 2. And then, of course, if both of the limits are the same, what is the limit? This should be just 5. The limit overall, of course, is 2. Thank you, because that's the justification. Oh, Dave said 1. 1 is the value, because the solid dot, we always looking like what curve is doing, and we looking where curve like meets, or like what, not the exact value. Everything near to that point. Okay, that's what I draw with the blue. We're just looking how the curve behaves, not exactly at this point. Exactly at this point we have value, it's okay. Okay. We will skip, I'm sorry, we will skip this exercise, but we will try to investigate this limit. Okay. Okay, that means how function 1 over x squared behaves at 0. Okay. Of course, I ask this way because now we know that we may have the situation that the limit is undefined. That means find the limit if it exists. Do you remember the graph of the function 1 over x squared? from lesson 1. Yes, one of the is the hyperbola. Yeah, do you remember the dance? Hyperbola in the first and the second quadrant. Okay. And what do you think? What situation we have? Definitely 0 is not in the domain. But that's not a problem for us because we're not looking exactly at 0. We're looking on both sides. That's what would you answer? How function behaves as x goes really, really close to 0. Okay, on the left and on the right hand side. How function behaves? That's what function does. What values the function is approaching? Do you think it's approaching a big numbers, huge numbers, of course, and of course we do have a special terminology we call infinity. And we do have a symbol, right? We do have a symbol. Okay, that's me. Now let's see. First of all, yeah, I do have some numerical values. Like when we substitute 1 or, I mean, positive or negative doesn't matter because we're squaring the numbers. That means it's even function, the same value for positive and the same for negative. But we can see I was trying to approach 0, 0.5, 0.2, 0.1, 0.05, 0.01, 001, and the values, of course, are huge. Okay, that's when we can say, yeah, we can say this. We can definitely say, because the same situation is happening on the left and on the right hand side. Okay, that means function does the same thing. But since the graph doesn't really like stop or doesn't really approach one finite number, I can also say that the limit is undefined. Limit does not exist as a one finite number. And both of the answers are correct. Okay, that means when I will create a multiple choice question, probably I can't put both of the options like infinity and DNE, because in this case this means the same. Okay? And as you remember, just 5 minutes ago I said as soon as we put that the limit is undefined, we have to have the reason, and that's the reason. In this case it's just infinity. But we will expect you to put infinity in cases like that. Right? But please just remember that it's the same. If somebody will tell you, oh, this limit doesn't exist, yes, correct. And then you can say, why? Oh, it's infinity. Yes. Yeah. Always we have to prove, right or wrong. Okay. And we just call infinite limit. Yeah, just probably obvious statement. Okay, but please remember, that's what I wanted to tell you. Yeah? The same thing. Don't argue with your friends, boyfriends, husbands, wives, girlfriends. Okay, let's do another one. Oh, another function. 1 over x, and we will investigate the limit at 0. That means what is happening with this function at 0 is also undefined, but that's not a problem. We're not looking at 0, we're looking on the left and the right hand side. And first of all, do you think will be will be worth it to check the left and the right hand side behavior? The left hand side limit and the right hand side limit? Okay, yes, thank you for typing. I'm just waiting, yes, for your, okay, x and y is missing. And of course, this is the left hand side, this is the right hand side. And as x goes really, really close to 0 from the left, the values, we can see, they go down. As x goes close to 0 from the right hand side, the values goes up, huge numbers. Okay? That means we will have positive infinity and negative infinity. That means what answer shall I put here? Does the limit exist? No, that means this one is definitely, this one is Yeah, that's we don't even have an option. And of course, if we decide to put this, we have to know, yeah, the reason. And the reason is, yeah, totally different directions, different limits. Okay, and I think, yeah, I have it. One thing I wanted, let me come back really quickly. You probably know this. As soon as because what we did check 0, okay? X equals to 0, the vertical line, because that's another definition, but I don't want to state everything as a like definition. When we investigate a limit at that point, and the limit is like we're getting infinity, we have a special name for that vertical line. Do you know how we will call that name? Because function is never touching this line. It's an asymptote. Is the vertical asymptote. Okay, that means if the limit is infinity at that given point, that point creates a vertical line and it's a vertical asymptote. Okay, that means the same situation is here. Doesn't matter for, of course, the limit, we do have different answer, but still this is a vertical asymptote. Okay, and then I do have a definition. The line x equals to a, yeah? It's just enough if you will get just even one-sided. Yeah? Even one-sided limit could be infinity, and then it's vertical asymptote. Okay, it's been just we will still get back to this vertical asymptotes, but just you know the definition overall, but just the limit definition. And that's the examples. We can see that means even if we have one-sided limits, infinity, it's still a vertical asymptote. We don't have to know the situation on the other side. Okay. Okay, that means that was everything like the intuitive definition, the meaning of the limits, different type of limits, infinite limits, one-sided limits, limit that is undefined, yeah, like oscillation, or two different one-sided limits. Okay, but now what we have to do, we really have to use our algebra skills. Okay, of course, we have to combine the meaning of the limit and the calculation. And now we have to know how to calculate the limits. Okay, let's start. That means we will definitely need algebra. That means what I can show you. I can show you a few properties, a limit laws. We will have a constant c, you will see a constant c, and you will also have, we will have a limit of the function f and the function g at a. And we're assuming that the limit exists for now, okay? That means what we have. When you will see the limit of the addition or subtraction of two functions, is simply the subtraction or addition of the two limits. That's mean limit of addition is addition of two limits. Kind of like a distribution, okay? If we have a limit of the constant, it's just the constant. Yeah? I can even give you an example. X, Y, I can use red. And for example, this is my function constant 5. That means what is the limit as x approaches 2? What will be the limit as x of the function 5? Yeah, we can see that's my, I don't even have, I can have my open dot, but function is approaching 5. That means for every number, yeah, it will be the same, the curve, the line is at the same level. That means, please remember, limit of the constant is just constant. When we have a limit of the constant times a function, we can like take out the constant outside and just focus on the limit. Of course, we have to probably do something, but we can keep that constant outside. It is still good property. When we have a limit of the product, it's just the product of two limits. That's perfectly fine. We can do this way. When we have a limit of the quotient, it's the quotient of two limits, but we have to just make sure that we're not getting 0 in the denominator. If we do, we will do something. And yeah, if we have a limit of the power function, we can compute the, first of all, like compute the limit of this inside value and then take the final answer to the power of n, like changing the powers, but that's, that's the same. And the same, did I type the root? Yeah, it's the same thing. When we have the limit of the nth root, I can compute the limit of the inside and then apply the nth root. Yeah, the same thing. Okay, and then, okay, that's me now. This is also important law, important property we call direct substitution property. I will read it for you and I can explain. If f function is a polynomial or rational function, okay, and a is in the domain of the function, that means because we sometimes looking at the limit at the number a, that a is not in the domain, but sometimes actually it is in the domain, okay? Then let's look at this. Limit of the function as x goes to a is exactly the same like the value. But of course, saying this, yeah, please always remember that they are not exactly the same. Do you remember that green 9 and the red 9? I can even draw it. Oh, that's just my pen. When I will draw x squared, and I think that the question was, let me put, the value at 3 is 9, right? We remember 9. But what is the limit as x approaches 3 of the function x squared? Can you give me the answer? Like, do you remember we did this yesterday? Like, what is happening as x goes really, really close to 3? What this curve is doing is, of course, it's approaching 9. Okay, that means that's what this property is telling. Because we have nice and continuous function, no gaps, no jumps, no asymptotes, x equals to 3 is in the domain of the function. Okay, then what I can do, I can simply take that value, substitute, and get this will be my limit also. Okay, that means if we have this situation, especially if the number is in the domain, I mean number must be in the domain, then the limit is the same like the value. But please always remember that behind this we have a definition, and like please feel that limit like meaning. Okay, but yes, and I think, yeah, we all like the direct substitution. Okay, and I think, oh, okay, and then I have, okay, oh, let me come back for a second. That's all of like the tools. And we, of course, we still need our algebra skills from previous math classes, and we will try to calculate, okay? That means let's start. First of all, I have a few examples. Too fast. I thought that I have the list. Okay, we just did this. That means what will be the limit of function x squared as x goes to 3? Can you just type it again for me? Yes, thank you. Because what I'm doing, I am directly substituting. Okay, 9. Then I have another function. X cubed minus x squared plus 2 as x goes to -2. This is polynomial. Polynomials are defined everywhere. That means -2 is definitely in the domain. In order to compute that limit, I simply have to substitute. Okay. I don't know how the function, how this function looks like. Can you actually compute the value for me? Lots of negatives. No calculators. Negative 2 cubed minus negative 2 squared plus 2. Negative 10. Negative 8, negative 4 plus 2, negative 10. Okay, I didn't know. I mean, I computed this before, but yes, thank you, Dave. Okay, that we can see like at negative 2, I don't know how this function looks like, maybe like that, maybe 2. But we can see at negative 2, simply the value is negative 10, but limit is exactly the same. But we know that limit means that the curve is just approaching that negative 10 level. Right? That means just, yeah, we understand. Okay. And then x times square root of x, how this function behaves at 9. 9 is simply in the domain. We can just substitute. Okay, that means that's no problem. Okay, can you tell me this number? Oh, come on. Yeah, you have to. Oh, no. Oh, yeah. Yes. 9 times 3. Okay, 27. For some reason, I was expecting 81. No. Okay, number 4. Oh, this one looks a little bit more complicated function. But is x equals to 5 in the domain of this function? What do you think? Yeah, that means what number is not in the domain? What number is not in the domain? Yes, that means we will have problem and we still have to know how to solve these problems. But we will have the problem if x will approach 3. But 5, no problem. We can simply substitute. 26 over negative 2, negative 13. That's what we can see. At least we know that at 5, yeah, function is like, I don't know exactly. I don't know how function looks like, but it's at least we know, and actually that's the location of the function. Like for 5, we have negative 13. Yeah, it's good information. We don't even have to know the whole function. Okay, and as x approaches 8, what is the limit of the cube root of x to the power of 5? Do you think we can manage without the calculator? We have to be smart. Yeah, this is one of the property, because we may. Of course, please do not do this, okay? Because I don't know if we can get 8 to the power of 5. That's huge number, okay? But what we can do, I don't know. But we can do this way. Yeah, do you remember? We can take this power outside. Yeah, that's the property of the exponents. And what is cube root of 8? Do we know cube root of 8? 2. Excellent. And what is 2 to the power of 5? I think we can manage. 32? 60. It is 32. That means, please, yeah, if you start producing huge numbers, then you can think, oh, no, something is wrong. She will not give me that huge numbers, okay? Okay, because of course, no calculators. Okay, let's keep working, because not everything will be nice like this slide. We may have situation like that. Okay, evaluate the limit of the rational function x squared minus 1 over x minus 1 as x approaches 1. Okay. That's me. What do you think? Can we really use the direct substitution? Not really, because what we actually getting? Can you tell me what we getting? When I did, we actually, yes, let me check. Oh, okay. We actually getting 0 over 0. Yes, thank you for typing this. And of course, looks probably so weird, But as you remember from yesterday's, like, I can say 0 over 0 is actually the main concept of calculus. Like, do you remember how to find out the slope of the tangent? Or the instantaneous, like speed, instantaneous velocity? Like when it's no run and no rise, 0 over 0, because we were trying to use I even have the slide, I copied the slide. Do you remember? We were using the limiting position of the slope of the secant line. And let's look at this. The point is 1, 1, 1, 1, right? And then we were getting closer and closer. And let's look at this. This is almost 0 over 0. Okay, and of course I can be even closer, 0 over 0. That means, because I can't really put 1 minus 1, it's 0. That means that's kind of like a main idea of computing, yeah, this type of limit. And mainly all of the limits that you will have, we will have 0 over 0, okay? Especially in this lesson, I think. Okay, but let's see how we can, what we can do, because we do have a, of course, algorithm. That means when you end up with this situation that substituting substituting a number, you're getting 0 over 0. Please remember, most likely the answer is not 0. Okay, because we can't divide. We can't divide by 0. That's one thing that you may maybe think it's undefined. But you can see we actually got 2. Yeah, of course, depends on the situation. That means it's almost, because this is almost 0 over 0. But we did have a situation, we did have some scenario, and we have 2. That means, please remember, 0 over 0 most likely will give me a finite number. That means on the multiple choice, don't select 0 right away. No. It's a rare cases that we may get a 0. Okay, that's what you have to do. Having a function, a rational function, numerator and denominator, we have to try to factor out, because substituting a number and getting 0 over 0, this means that they have something in common. Okay, the numerator and denominator, they have something in common. We have to factor out, find this common factor, cancel out that 0, and then we will be able to use the direct substitution. I know it's easy to say, but let's come back to this question. What do you think? What algebra we can use to find this common factor? Do you think we can factor out x minus 1? We can't do anything. But what about x squared minus 1? Do you remember that? Yes, of course, Dave. We have a squared minus b squared. I can factor out as a minus b, a plus b. Okay, and then can you see the common factor? 1 minus 1, 1 minus 1, that's my 0. And the 0 is gone. And actually, after reducing, I can substitute. Instead of x, 1, and it's 2. But we still have to remember, function is not defined. X equals to 1 is, I should say this way. Function is still not defined at 1. Do I have the, no, I don't. I can draw this function, a little bit here, because we managed to, from that formula, we managed to simplify and we get x plus 1. X plus 1 is just the line. Yeah, if I will think as a function, it's just the line with the slope 1 and y-intercept 1. That's that's 1 also. Okay, but what is important? At x equals to 1, we have no value, okay? And just the limit. We know that is at that open dot is at the level 2, because that's my limit, but it's no value, it's open, it's not solid dot. Okay, that's me, please remember, but that's the way to do it. Okay, 0 over 0, and we again get limit 2, like from that slope. Okay, that means let's keep working. What I have a nice, beautiful reference slide, and I'm afraid that we have to, that's algebra, but we have to know all of these formulas. Okay, we just use this one. Sometimes we have to like expand the form, or maybe from the expanded we have to write as a square of the, like a perfect square, completed square of the addition or subtraction. Also, we have to be able to expand the cubic expression, addition and subtraction, and also this. That means please make sure that you will remember these formulas. Okay, we will not go further, just cube, not the fourth or any other higher power. Okay, that means that's probably the slide to print off and maybe take the notes. Okay, let's see. Example number 3. Really nice, almost the same concept that we just did. Find the limit as x goes to 3 of the rational function x minus 3 over x squared minus 9. We can see right away, when I substitute 3, I have 0 over 0. And function is not defined at 3. That means what we will do, we have to rewrite, find the common factor, common 0, cancel out, and then substitute 3. Do you know how we can rewrite this expression? Who can tell me? This one. How can I rewrite? Because that's what, of course, x minus 3, x plus 3. Yeah, and do we see the common 0? The common factor? That's my 0, that's my problem. And the answer is 1, 6. Okay, that means again, it's just, this is just the limit. When we will draw this situation, at 3 will be 1, 6. Okay, I don't know exactly, let's say, I can probably draw the function, but it's just the open. This means that the limit is 1, 6. Okay, and the rest of we don't have to draw it at the moment, no. But I just want you to know what exactly is this. Yeah, this is always the y value. Okay, let's see. That means what I have lots of examples in this. Okay, in this presentation, and I don't know if you checked the live session recordings, because I saw, because when we will finish at 9 today. That's mean I will not keep you, because probably in order to solve all of them, I have to keep you, I don't know, until midnight. I will not, but we will finish at 9, and if I will just stop wherever we are, but please check, because I did put the recording, the video of me solving all of the problems which are in this presentation. Okay, that's mean if you didn't see, because I did post the video yesterday. Okay, yes, okay, thank you, Sarah. That means when something is not solved, please check the video. Okay, because and if you will know how to solve all of these limits, you're perfectly fine for this week, for this lesson assignments. Okay, but let's keep working. We still have like 10 minutes. Okay. Oh, that's the cube. Okay, limit at 1, and then x cubed minus 1 over x squared minus 1. That means substituting 1, we're definitely getting 0 over 0. But what we will need a cube minus b cube. Okay, this was the slide with the formulas. This will be a minus b, and then a squared plus ab plus b squared. Yeah, we can see it's a little bit different, but that's the way to expand it. And of course, the denominator is squared. That's easy. Everybody knows this. Okay. Oh, I didn't type the answer. Let's type it. That means we will have x cubed minus 1 over x squared minus 1. They definitely have common factor. Okay, that means x cubed minus 1 cubed. It will be x minus 1, and then x squared plus x times 1 plus 1 squared. And then x minus 1, x plus 1. Okay, and we can nicely see that's the common factor, that's the common 0, gone. What is the answer? Who can tell me? Can you type for me? Thank you. 3 over 2. But please know the formulas, okay? And it's just the formulas that I typed for you. No other like surprise, no. I mean, it's never surprise. Okay, example number 5. Okay, let's skip that cube. Yeah, you will check that video. I did solve it because it's the same idea. I just wanted, yes, I want this. Because for this one, we don't really need a formula. We just need a little bit of algebra skills. Okay, algebraic function, the ratio of square root of x minus 5 over x minus 25. When we substitute 25, of course, 0 over 0. What we can expect in the calculus class. No rise, no run, 0 over 0. But we do have definitely common factor at that 25. That means what we can do when we see like a square root expression, right? We do have a way to rearrange, to rewrite this expression. Let me check. Okay, that means this is, and that's important. Please remember, we will, in order to rewrite, because we can't really factor out unless you really see this. Because I always have 1 or 2 students, they kind of see, which is also good, but I will give you like more, a little bit, I believe, a little bit easier way to rewrite this. Again, when you will see the square root expression, we will multiply the denominator and numerator by the conjugate expression. And I hope we know what conjugate is. Like, let's say we have square root of x minus 5. That's the expression. That's the square root expression. I will say that this is a and this is b. Conjugate expression is just the same a, the same b, but plus. Okay? That means x square root of x minus 5, square root of x plus 5. And since I am multiplying the numerator, I have to multiply the denominator to keep the original function. Okay? That means this is the conjugate expression, plus 5. And of course, we just know a minus b, a plus b is just a squared, b squared minus. Can you tell me how can I multiply? How can I distribute square root of x minus 5, square root of x plus 5? I will square the square root of x. What I can get? Just x. And I will square 5. 25. Okay? Oh, I didn't. That means we can see. From this, I have x minus 25. And did you notice I didn't distribute the denominator? And do you think why I didn't distribute the denominator? The expression in the denominator, why I didn't multiply everything, this times this times this, like normally I will do it. Do you see why? Because because then we will come with the common factor. Yes, x minus 25, I will spread out and I will not see. If I will have the expanded form, my x minus 25, which is the 0. That's the 0 because we're looking at the situation, I mean the limit as x approaches 25. That means I will lose that 0 completely. That means that's the reason that we have to, when we decide to do this way, only the conjugate expressions we have to multiply, not the other. The other stays as a product. Okay, and of course, do you know the final answer? That's my 0. I found the common factor. The 0 is gone. And the answer is, who can tell me? 1/10. Excellent. Okay. Okay, that we can see the square root expression, we will do like that. And let's do maybe one more, okay? Let's see. That's the square root expression. I will leave it for you because you can do exactly the same way. Oh, do I have the solution? Don't look at the solution. I mean, you can check later, but I did exactly the same way. I multiply by the conjugate, I rewrite everything, common factor, cancel out, and direct substitution. Okay, for example, something like that. Limit at 0 of x plus 3 squared minus 9 over x. That means this is just the rational function. Okay, and the only thing that we have to do, probably we have to expand this. Okay, because it is 0 over 0. Okay, it is 0 over 0. I'm just checking. That means what we will do. Yeah, because that's the case that we have to just use the algebra. X plus 3 squared, or I can say a plus b squared. It will be a squared plus 2 times ab plus b squared. That's we have x squared, 2 times 3 times x, and 3 squared, 9. And then minus 9 over x. And let's simplify. First of all, I can simplify this. Correct. And we have x squared plus 6x. Do you think I can factor out x? And do you see that common factor, that common 0? The common 0 is gone. What is the final answer? Who can tell me at the end of the session? It is 6. And as I said, I have more questions, but all of them will contain probably some formulas or just simply like a basic algebra. Some common denominator probably, I have probably the next one, or the square root expression. Remember about the conjugate. Okay, that means that's everything what we have to know. We have to know how to compute the limits. That means please check the additional video. I think I call practice with Kasia. That means you can check practice with Kasia videos. And if you will know all of the limits that I solved, you will ace it, everything what is required this week. And please, of course, please keep posting something on the discussion board, okay? Okay, thank you for joining me. Thank you for answering all of my questions. And yes, have a good night. Thank you. Thank you. Thank you. Thank you, Dave. I mean, thank you everyone who was typing and who was participating. Thank you.